Hello students, welcome back to this module number 20. Over here we are going to learn about the very famous Geiger-Nuttal law. We are going to understand about the alpha spectra and fine spectra in the alpha spectra and about the short range and long range alpha particles. Okay, at the end of this module you are expected to understand and know a lot about Geiger-Nuttal law, at least the basic of it, and the alpha spectra and the fine spectra, what do they mean, what they are, how do they exist, and also about the short range or difference between the short range and the long range alpha particles. Okay, so to begin with, let's start with Geiger-Nuttal law. Okay, so the Geiger and the Nuttal together collected a lot of experimental data, the range of the alpha particles, the disintegration constants and so on. They collected this and then they plotted the graphs. Okay, they tried to analyze this and they started to study it, and this was way back in 1911. Okay, and what did they observe is that that the longest lived nucleides, had least energy, had very less energy of alpha particle, whereas the one which lived for a very short time had high energetic alpha particle. Okay, I hope you are understanding this. Okay, the nuclide which lived for a longer time had a lower energy alpha particles, whereas the one which lived for a shorter time, okay, had very high or very energetic alpha particles. All right, that is expected. For example, if I give two people same amount of money, if one person spends the money very fast, of course his money is going to get over very fast, and the one who spends slowly will have money for a longer time with him, right? So same way here, we had a nuclei which gives out very high energetic particles, so they don't live for a long time, they get decayed very fast to the daughter nuclei, to the ground state rather, whereas the one which had lesser energy particles, which used to give out lesser energy particles, stayed for a longer time and to come to the ground state. Fine. So when they plotted this data that they had of these different radioactive material that they have, and they plotted the data, what they got is a very straight line. Okay, what they got is a very straight line. They plotted it the log of lambda, that is log of the decay constant, versus log of the range of this alpha particle, and when they plotted this, they got a very straight line. Now mathematically we know the equation of straight line. Equation of straight line is y equal to mx plus c, right? Now what is there in place of y here? We have log lambda plus 20. 20 is a constant which can be put in the constant side, so we will have log to the base 10 of lambda equal to mx, so m is the slope, so that is b, and x is a log r, the base 10, okay, plus a, which is in place of the constant. So it's a straight line. So the slope of all three series, it is plotted for uranium series, thorium series, actinium series here. So the slope was almost same for all three series. It's not much difference, but there were a lot of differences in the constant, that is a. Okay, so this is the plot that the Geiger and Nuttal got. And that's what the law was also about. Okay, so the law was that the log of lambda was of the alpha decay was equal to the log of the range, okay, plus the constants. Okay, that's what the law of Geiger-Nuttal law states also, and it's a straight line. Okay, and it's a straight line for all three series that you can see here. Now, according to the Geiger law, the range is also directly proportional to the cube of the velocity of the particle, okay, velocity of the emission of the alpha particle. The range was directly proportional to the cube of the particle. Now, if I have to get expression for range in terms of energy, so we have to first understand how energy is related to the velocity. So as you can see, energy is half mv square, so energy is directly proportional to the square of the velocity, whereas a range is directly proportional to the cube of the velocity. So first of all, I need to write this velocity in terms of cube. So what I do is I find the square root. So I get square root of E equal to directly proportional to V, and then cube on both the sides. So I will get e raised to 3 upon 2 directly proportional to the cube of the velocities, and then substitute it back in the range. So I'll get range is equal to directly proportional to e raised to 3 by 2. Okay, now if I find the log of this, I'll get log of the range directly proportional to 3 upon 2 log of e, where 3 upon 2 can be written as some other slope b prime instead of b, and we can rewrite the Geiger-Nuttal's law in terms of energy. So we have now Geiger-Newton's law in terms of the range of the alpha particle, as well as we have the Geiger-Newton's law in terms of energy. Okay, we have both in terms of the range as well as energy. Next, what we have is the alpha particle, then fine structures that is related to it. Okay, so till now we have implied that every alpha emitter has only one associated alpha energy, right? And also it looks very obvious that yes, there is a material which is emitting alpha particle, and since there is the only material there, it will have its initial state and the ground state, and of course I expect only one energy level, right? That it looks very obvious. Okay, and this is also expected, right? Because you, as I said, you will either have a parent nucleus and the daughter nucleus. That's how we have been writing the equations also. We have been writing the parent nucleus on the left side and daughter nucleus, and then emission of alpha particles. So it looks as if you're going to have only one kind of energy that will be carried, that will be followed. However, that is not true. Okay, here I have an example for you of polonium getting decayed to lead. Okay, and when this occurs, there are 4 group of alpha particles having range of 6.91 centimeters, 7.79 centimeter, 9.04 centimeter, and 11.51 centimeter. Okay, so it shows that this decay is showing 3 different types of ranges of the alpha particle. Okay, the alpha particle is getting, as it's moving in the magnetic spectrograph on the photographic plate, the range is showing collection at 3 different points. Okay, it's having 3 different collection can be seen. The ranges are different, and of course, since the range is different, obviously the energy associated with also be different. As you can see, there are 3 different kinds of energy also that is associated with this decay. Another example that I can give you, which is a very popular one, which is a decay of the thorium. Okay, and as you can see, this is a very nice one with the energy level diagram for you. As you can see, this thorium is getting decayed to radium. Okay, and as it is getting decayed, it is having 5 energy level. Of course, the most probable one is 5.42 mega electron volt with almost 71% of it most dominating, followed by the 5.34 mega electron volt with almost 28% of it, and rest of it, its contribution is very, very low, but it does exist. Okay, so we have this emitted, so that shows that there are fine structures, and it is not just one energy level that is existing. There are many multiple energy levels existing, and only few of them are coming down to ground state. Some of them are still on the excited state. You can see this one is still on 84.5 kilo electron volt energy level. It's not still come down to ground level. Only those which will come down to ground level will be giving out gamma radiations. Okay, it will give out gamma radiations and come down to gamma or to the ground state. Whereas these ones which are on excited state may give some more alpha particles, to come down to ground state. Okay, so now what you are seeing is the short range alpha particles. Okay, and in case if these ones which are still on excited state gives out more alpha particle to come down to ground state, then they are called long range alpha particle. Alright, that's the difference between short range and the long range alpha particles. Okay, so if you have the parent alpha emitters emit the alpha particle when it is in an excited state, then we get a long range alpha particle. Okay, so a long range alpha particle would use or utilize the energy from the excited state as it's going in the ground state, and the addition of these 2 energies will give you very long range of alpha particles. Okay, now this is because the energy of excitation becomes available to the alpha particle as they reach to the ground state of the daughter nucleus. Okay, just a very simple example that I have for you is again of polonium getting decayed to lead, and as you can see, the alpha particles are given out from these excited energy levels itself, and you can see the energy that is associated with it, almost 10.75 mega electron volts, 9.67 mega electron volts, 8.95 mega electron volts, and so on. And now compare it with the short one that we had, it was 5.14, 5.17, something in the range of 5. And then you have the long range alpha particles, of course from a different material, that is polonium and lead, but you see the range of this alpha particle is almost, I mean the energy that is associated with this alpha particle is almost double of the one that we had got from the short range alpha particles, correct? So that's it. Again, I have referred to S.B. Patel for this lecture. You can refer to some more books if you want out of your choice. Here are the books that is been recommended for you to refer. Okay, so see you for the next module. Right? Thank you.